In this lecture, we're going to look at a very different style of creating large systems. The style is called object-oriented programming, and it focuses on breaking systems up in a different manner than what we've seen prior to this. To set the stage for this, we're first going to go back and look at the notion of abstractions, use that idea to see how we can capture objects with some internal state that reflects the status of those objects and how to manipulate that. And we're going to be led from there to a style of programming called message passing, in which we treat systems as if they consist of large collections of objects that communicate with one another to cause computation to take place. Let's start by going back and thinking about the tools we've developed so far for thinking about computation. Two of the key ones we've developed have dealt with abstractions. We've seen procedural abstractions. Here the idea is to capture a common pattern of processing into a procedure, then isolate the details of the computation from the use of the computation by simply naming the procedure and using it with appropriate conditions on its input. We saw that this style of approach is particularly useful when dealing with problems that are easily addressed in a functional programming approach. That is, where we can treat the procedures as generalized mathematical functions, meaning that their output for a given input will be the same whenever we evaluate it. We've also seen data abstractions. Here the idea is to modularize our system by creating data structures that capture key parts of the information we need to handle. The goal is to hide the details of the representation and storage of the data behind standard interfaces, primarily our constructors and selectors. This means that the user can then manipulate data objects without having to worry about details of how they were maintained. As we might expect, often the data abstractions and the procedural abstractions go hand in hand, with the procedures used to manipulate the data using the data abstraction interfaces, and with the structure of the procedure tending to mirror the actual structure of the data. The goal in each case is actually the same. We want to hide details of the abstraction so that we can treat complex things as if they are primitive units. In the case of procedural abstractions, we want to hide the details of the computation and treat the procedure as a primitive computational unit. In the case of data abstractions, we want to hide the details of how components are glued together and treat each unit as an abstract collection of parts. Given that we want to use abstractions as a tool in controlling complexity in systems, there are several questions that come up when thinking about how to use abstractions. The first is, what's the best way to break a new problem area up into a set of modules, both data modules and procedure modules? As we've already seen in earlier lectures, some problems break down in multiple ways, and breaking them down in different ways makes some things easier and other things less easy. So a key question is, how do I use the idea of abstraction to break systems into modules, and what's the right way to do that? And the second set of questions we ask basically deal with how easy is it to extend the system. If I want to add new data types to my system, is it easy to do or hard? If I want to add new methods, new ways of manipulating data types in my system, is it easy or is it hard? We've seen several examples of this already. We're going to come back now and look at those questions in order to lead to a very different way of breaking big systems up into convenient-sized chunks. Let's start by going back to data objects and data abstractions. Here's the traditional way of looking at data, at least as we've done it so far. First, we build some complex data structure out of primitives, for example, const cells or pairs. Secondly, we use tags to identify the type of structure being represented. This tells us how to interpret different slots in the list structure. For example, is the car of the list structure the name of a person, or his batting average, or his GPA? Then, the data abstraction is actually built by creating a set of procedures that operate on the data. That is, these are procedures that take in instances of the data, use selectors to get out the pieces, do some manipulation to create new pieces, then use a constructor to reglue the abstraction back together. This led to the concept of data-directed programming, which we saw earlier. Use the tag to determine the right set of procedures to apply. And this, of course, allows the user to program in a generic fashion. They can just think about what they want to do, but have the code direct the data to the right place for the actual work. Here's a simple little example to illustrate the point. Suppose I have a set of different arithmetic objects, there's particular geometric objects, things like numbers, lines, shapes, other such things. And I want to write a procedure or an operation that will scale each of those objects by some amount. Then a generic operation under the data-directed programming style would look like the procedure shown here. Given an object and a scale factor I want to scale by, I use the type of the object to dispatch. If it's a number, I just multiply it out. If it's a line, I ship it to the thing that will scale a line by the right amount. If it's some arbitrary shape, I ship it off to that thing. And shape scale, for example, might have different procedures for different kinds of shapes, so there's a second level of data direction taking place here. The point of this example is that I think about things in terms of here are the kinds of objects, and my procedures for manipulating them use the tag on the type of the object to tell me what to do and who to send it to. Okay, now let's go back to our questions. How easy is it to extend such a system where we're breaking things up in terms of tagged data and using data-directed programming? First, if we add a new data type to our system, what do we have to do? Well, we can see from this example here, we're going to have to go through and modify all the procedures like this. We're going to have to add a new clause to each cond dispatching off to that new type. And as a consequence, if there are a lot of such things, we've got a lot of changes to make. Both a great deal of code to write, and more importantly, making sure that we make changes in all of the appropriate dispatches. If we add a new operation or method, what do we need to do? Well, in that case, we just need to develop a sub-procedure for each relevant type. So, it says in this kind of programming, the first part's painful, adding a new data type to our system. The second part is not so bad, in that case, adding a new operation or method. As a consequence, this approach, this idea of breaking things up in terms of tag data, dispatch on type, this approach works best when there are a small number of data abstractions, or when the changes are mostly new methods or operations, or when the different kinds of data structures in the system are very independent or unrelated to one another. In those cases, this style of approach works pretty well. But of course, we know not everything fits that kind of framework or paradigm. So what do we do when we have problems that don't obey this kind of a model? So let's step back from this organization for a second. One way to think about structuring a large system is to realize that we are likely to have a large number of different data objects, or instances of data abstractions, and a large number of operations we want to perform on those objects. Conceptually, this means we have a big table, where we can use a different row for each operation we want to perform, and a different column for each kind of data abstraction we have. Then, at each element of this table, we can conceptualize having a specific procedure intended to perform the particular operation, for example scaling, on the particular kind of data object, for example a number. One way of actually building such a system is to focus on the rows of the table, or in other words, the operations. Indeed, our use of tag data was based around this viewpoint, in which we created generic operations that handled the same operation for different data objects. And we used the tag on the data object to dispatch to the appropriate version of the procedure to handle that kind of data. But given this table, there is an alternative possible organization, which is around the columns of the table. This would focus on creating a generic data object that would know how to handle different kinds of operations for a particular kind of data structure. Well, let's step back and rethink data. Sounds like an odd thing to do, but let's think about data in a very different way. In particular, rather than thinking of data abstractions as a structure with some slots into which we can put things, let's instead consider data to be a procedure with some internal state. Whoa, that sounds strange. Well, first of all, what is a procedure? Well, it really has two parts. It has a set of parameters in a body, the things that are specified by the lambda expression, which say what things you should be able to pass in and what you want to do when you do that. And as we've seen in the environment model, it has an environment associated with it, which can hold name-value bindings, that is, pairings of names and values. So what, you say? Well, we can actually use this idea to capture information about a data structure. In particular, we could use a procedure to represent a data object with some state. What would that mean? It would say that we could use the local environment of the procedure plus its parameters to hold the values of the data object. And secondly, we could create local procedures within the procedure to manipulate those values, to change the state of the object, to change the values associated with the data structure that we're representing this way. This means that the only access to the values held in the environment of the procedure would be through the procedure itself, so we would be nicely encapsulating that data structure inside this procedure. This sounds like a lot of words and probably still sounds kind of odd. So in the next set of slides, let's look at an example to see what we mean. To illustrate this idea of using a procedure to represent a data structure, an object with state, let's look at the following rather odd example. Here's a very different way of implementing a const cell or a pair. And let me stress, this is not the way it's done inside of Scheme, although you should know by now that the idea of data abstraction says you shouldn't really care and probably shouldn't be able to tell. But it drives home a conceptual point. So what do we have here? We've implemented a pair as a procedure, and thus our fundamental data structure is now a procedure, not some storage and memory slots. So let's look at this carefully. First, note that const, as defined here, involves two lambdas. Remember, there's a hidden lambda inside the syntactic sugar. This means that there's a second one then in the body of the const, and thus when we evaluate const of xy using this particular implementation, we get back as a value a procedure of one parameter, MSG or message. So what does this say? It says when we use const using this implementation, the thing we get, the representation for our fundamental way of gluing things together, is now a procedure. It's a lambda of one argument, MSG. Now, what would that const thing do, that value we get back? Since it's a procedure, if we send it a value, or apply it if you like to an argument, note what it does. it uses the value of the message. In this case, it better be a symbol of a particular kind. It uses that value to decide what value to return. We call this style of programming message passing because the procedure here accepts a message and then does something based on the particular value of the message it got as input. So this looks a bit weird. Our constructor now, for gluing things together, gives us a procedure as the actual object. But should we care? Well, we know we shouldn't, right? To complete the abstraction for a pair, we know what we need to do. We just need to create car and cooter to fulfill the contract of the abstraction of a pair. So each of those is itself a procedure that takes as input a pair, which we know is a procedure, and then applies that procedure to a single argument, which in this case is just a symbolic message. And ideally, that message should get us back the value we need to satisfy the contract. And indeed, if we look at the definition for car, it's taking as input one of these pairs, which is a procedure. And what does the body of car say to do? It says pass that procedure the message car, the symbol car, which in principle should then give us back out the value we used when we glued the two things together. Note the other procedure we built here. Our predicate for testing whether something is a pair now relies on the pair identifying itself. This is equivalent to our earlier tag. Or in other words, before, we attached a tag as a symbol to a data structure. Here, our tags are procedures that identify the kind of object. Okay, let's check it out. Let's take this rather strange implementation for a pair. A pair is now represented as a procedure, and let's see if it does the right thing. So let's use it. Let's const together the numbers 1, 2, and give them the name foo. So here's an environment diagram that would represent the state of the world before we do this. In the global environment, we have a binding for const. It's to this procedure, as we just saw in the previous slide. So what happens when we evaluate this? Well, const is just a procedure. So evaluating the sub-expression const 1, 2 says, take the value of const, which is a procedure, and apply it. Therefore, drop a frame, scoped by the same place the procedure is. Inside that frame, bind the parameters x and y to the values 1 and 2, the input parameters, and relative to that new environment, evaluate the body of the procedure. And that body is itself a lambda. So it makes a new procedure object. Notice the environment pointer points to the frame E1 because that's the environment in which I was evaluating it. And then that entire procedure is returned as the value of the const. What else happens? Well, then we define foo in the global environment, which is where we were doing the original evaluation. We bind foo to point to that object, that procedure. Notice what this does. It gives us an object in this environment, where by object I mean the thing enclosed in red here. It's a procedure that has a local frame with some bindings or values in it, some state information. X is bound to 1, Y is bound to 2. That is itself scoped by the global environment, and is referred to by a name outside of it. Thus, from the perspective of a user interacting at the global environment, foo refers to a structure that has within it information. Information about what the first part of the object is, 1. Information about what the second part of the object is, 2. And it should, if we see in a second, have information about how to get that data back out. So this pattern, this capturing of a procedure that takes in messages, has associated with it an environment frame with some local state, and some messages that allow us to get different information out of that state. This particular structure is a very common pattern that we're going to come back to. Now all we have to do is check that the contract holds for this data abstraction. And in doing so, we'll see how this structure, this object of a procedure that accepts messages and returns information, actually captures what we want. So, let's evaluate car of foo. Looks like a normal expression. We know it should get converted into sending this object foo the message or symbol car. But let's see how that actually happens. Or said another way, evaluating car of foo in the global environment says get the values of car, which is a procedure, and the value of foo, which we see as this procedure, and apply the car procedure to this argument, which, as we saw, converts this into evaluating foo with the message car as a symbol with respect to some new frame. And what does that do? It says apply foo, which is a procedure. So just by the standard environment model rules, we drop a new frame scoped by the same frame as the procedure is. And that's important because this frame E3 now points into E1. Inside that frame, we bind the parameter MSG to the value passed in, which was car, and relative to that frame, we evaluate the body of this procedure represented by foo. That, as you'll recall, is just a big con that looks at the expression, the MSG in particular, to see what symbol is it. In this case, it says return the value of x with respect to this frame. And what's that? That's just 1. So I'm set. I return out the value 1 exactly as I want it. So what does all this say? Aside from showing that our contract holds, that what we glue together with const we can get back apart using car, and obviously coded the same way. Besides showing that, we've also now seen this common pattern, that we can create a data structure, a data object, represented as a procedure. The procedure has some local state captured in a frame that's accessible only by that procedure, and it has the ability to accept messages and based on those messages return information from the local state. So let's see how to build on that idea. Okay, so we've seen how to create a data structure as a procedure that has some local state in it. And in this case, what we saw was that the procedure could accept messages and return values, values that represented either the value of the state or something that we could potentially compute off of the state. Now, if we're going to use this idea of message passing procedures to represent information, we also need to have ways of changing the value of the state captured by that procedure. In our pair example, here's how we do it. Let's add two more messages, or two more ways of dealing with messages, to our constructor cons. One for dealing with mutating the car, one for dealing with mutating the cooter. And notice in this case it's a little different. If a cons pair, one of these procedures constructed by cons, gets the message set car bang, we're going to return a procedure. A procedure that then says, give me the new value for car, and I'll make the change to change my old value of car, which remember was x, to be that new value. And similarly for set cooter. So now a little bit different behavior. Here, a message gets us back a procedure, rather than just a numeric value. As a consequence, the procedures set car bang and set cooter bang have to have a slightly different form. As before, they're going to take in a pair, represented by one of these procedures, and a new value, but now they send the pair, that procedure, the message set car bang, it gives us back a procedure, and we then apply that to the new value, hence this rather unusual form. So let's see how this works. Here's a definition of bar. We're going to define bar to be the cons of 3, 4, and here's the global environment in which we're going to do that. And what happens when we do this? Well, just like we saw before, applying cons will create one of these structures, a procedure that takes in a message as parameter and has a body that does things based on that message, and it contains within it a local frame in which x is bound to 3 and y is bound to 4. And then, of course, bar is defined to be that value, so it points to the procedure from the global environment. This structure is just like what we built before. There's one of our message passing objects. So now, let's mutate it. Let's change the car part of bar to be 0. And as we saw, evaluating this expression, set car bar of bar to 0 in the global environment, comes down to passing to bar the message set car bang and applying whatever we get from that to the value 0 in some frame. This just comes from the code that we had on the previous slide. What we want to see is how evaluating this expression causes the right thing to happen. So we need to evaluate that expression, which means we first have to get the value of the sub-expression open param bar, quote, set car bang, close param. Oh, that's okay. What's the value of bar? It's up there in the global environment. I trace it up and I find it, and I'm going to apply that to the symbol set car bang. So that drops a frame who's scoped by the same place as the environment pointer part of the procedure is. So notice, E6 points into E4. Inside of that frame, we bind MSG to be the symbol set car bang, as we'd expect, and relative to that frame, or that environment, we evaluate the body of car, which is that big long cond expression. And what that is going to do, as we've seen, is give us back an expression, lambda of new car, set bang x to be new car. Now here comes a critical point. Remember, we're evaluating the body of bar with respect to E6, which got us down to saying, gee, given that the message was set car bang, evaluate this expression, open paren lambda, a bunch of stuff with respect to E6. What does evaluating a lambda do? It creates a procedure object. But the crucial thing is, what's the environment pointer part of that object? Ah! It points to E6 because that's where I was creating it. So I create this procedure object with one parameter new car and a body that's going to do the right thing, but with the environment pointer part pointing into E6. That means that this procedure has access to E6 and therefore E4 and therefore GE. And this procedure is literally the value returned by evaluating open param bar of quote set car bang close param. And of course this is exactly what I want, because now what do? I'm evaluating, remember, that expression up at the top, so I'm going to apply that procedure or that value to the argument 0. And what does that say to do? Just substitution model. I drop a frame with the parameter new car, that is the parameter of this procedure, bound to the argument 0, and notice this frame points to the same frame as the procedure object did. So E7 is scoped by E6, which is scoped by E4, which is scoped by the global environment. I have a nice chain of frames here. Relative to E7, I evaluate the body of this procedure, which I just made, and that says do a set bang of x to new car with respect to the frame E7. So now we evaluate that set bang x to new car expression with respect to E7. And here the rules say, gee, find the binding for x. Start in E7, trace up through E6 to E4. There it is. Find the binding for new car starting in E7. It's 0. So go up to that place where x was bound and change it, removing the old value 3 and replacing it by 0 in the appropriate frame. And the key thing to notice, if we step away from all these details, remember that little squiggly structure around that object bar, which was a procedure that took messages and had some internal state? Notice what the state looks like now. Now I have the first part, x, which is the car part, as 0, and the second part, y, which is the coulter part, as 4. And so we see, with this idea of a procedure capturing local state, not only can it return information about state, but if we send it a message, it can give us back a procedure that causes changes in that state, allowing us to mutate our pairs. So this is certainly very different from things we've seen before. Now we have data structures, data objects, that are actually themselves procedures. A const pair is a procedure. A car is something that operates on one of those procedures. But as we've seen, the const, car, and coulter we've just built satisfy the data abstraction and therefore behave appropriately. The key thing is that we've now built this new idea into our language. A data structure is now a procedure. It takes a message as input, and in this case either returns a data value or a procedure to handle a data value in order to make changes. This turns out to be a very handy idea, so let's generalize it. In particular, let's create both private state variables, as we've done before, but also private procedures that belong to each instance of the data abstraction. So notice the difference here. Now I create internal procedures, change car and change coulter, things that are going to do the right thing. But inside of my actual object, I not only create those procedures, I use them. This has a very nice effect. If you look down at the bottom, it says when I want to actually do something, I don't have to remember what kind of thing is returned and what to do with it. The use of these procedures is exactly the same. Or said a little better, it makes selectors and mutators perform in a uniform way. Before, we had to remember whether the object returned a value or a procedure in order to complete the process. Here, the selectors and mutators just send a message to the object, and within the implementation of the object, we take care of the necessary work to either apply a procedure or just extract the value. So the internal procedures here make sense. And notice, by the way, by defining them within the context of the const, remember that these definitions will create procedures that are scoped within the frame created by the calling of the const. Or said a little bit better, it means these procedures belong only to this instance of const. What else do we have, though? Well, by making this uniform application of mutators and selectors, we've introduced one more thing into our system. In particular, we need our selectors and mutators to deal with different numbers of arguments, and yet we want our data abstraction to be a single procedure. So we need a way of letting a lambda object specify that it wants to take an arbitrary number of arguments. And that's that funny notation of lambda of open paren msg dot args close paren. And on the next slide, we're going to come back to that. Up until now, every procedure you've written has required that you specify names of all the input parameters it's going to take. And as you've seen, if you call the argument with the wrong number of input parameters, it causes problems. We'd like to have a mechanism that lets a procedure take an arbitrary number of arguments. And in some sense, you've already seen that with some of the built-ins like plus and times. We'd like to have something, say, add, that can take 2 numbers and do the right thing, or 4 numbers and do the right thing, or arbitrary numbers of numbers and do the right thing. So Scheme provides a way of doing this. And let's look at the definition. Let's define add of xy.rest to be a bunch of things. Here the syntax is an argument x, an argument y, and then a dot, and then the argument rest. And the behavior is as follows. It says when we apply add to a set of arguments, the value of the first argument will be bound to x, the value of the second argument will be bound to y, and the values of any remaining arguments will be bound as a list to the argument rest. Thus, if we add 1 and 2, x is bound to 1, y is bound to 2, and rest is bound to just an empty list. If we try and add just 1, we'll get an error because the first 2 arguments are required. I have to have something for both x and y. But if we add 1, 2, 3, x will be bound to 1, y to 2, and rest will be bound to the list 3. And if we add 1, 2, 3, 4, 5, you get the idea. Rest in this case will be bound to the list 3, 4, 5. Thus, in this particular notation, all of the parameters prior to the dot require a specific value. The parameter after the dot will be bound to the list of the values of all the remaining arguments passed in. So if we come back to our example, we see that if we just take the car of a pair, then MSG will be bound to the symbol car, and rest will be the empty list. On the other hand, if we want to set car the pair, then MSG will be the symbol set car, and args will be a list of one value, the new value to be used. within the procedure that defines the const, notice what happens. If we're going to do a set car, we apply the procedure change car to the first argument in the list args. In other words, it'll get out the right new value and cause the appropriate change. It will mutate the binding of x to be that new value. And thus we can apply these internal procedures to the right values to cause the right changes to happen. Since we've been throwing a lot of details at you, let's step back from this. What we've now seen is a method, using a particular example, but a method for creating a procedure that captures local state. This procedure takes in a message, and based on that message and possibly some other arguments, it either returns values based on the local state, or it causes changes in the values of those local state variables. This new method, this idea of a message passing procedure, lets us capture information about a data structure inside a procedure itself. So what does this say? Well, what we've done is introduce the basic idea of a new style for approaching computational systems. Our traditional style is procedural programming. We organize the system around the procedures that operate on the data. The key here is that we isolate the data in standard list-like structures with tags, then focus on thinking about what methods or procedures we want to use to manipulate the values within those structures. Here we've shown the basis for a new approach, which is oriented around the data objects themselves. Note what we did with our example of a pair. We focused on capturing the information within a structure where the operations to manipulate the data values were associated directly with that structure. More importantly, the basic conceptual unit for thinking about a system is the object itself. What things should an object do, i.e. what messages should it handle? How do we want to capture those methods internally within the object? Now, which approach is better? And the answer is it really depends on the problem domain. Procedural methods are very good when we're dealing with things like numerical operations, or when we're dealing with systems with very small numbers of data structures. On the other hand, object-oriented systems are very good for things like simulation, or for systems with large numbers of objects, where the objects themselves are characterized by a small amount of state information, and the computation basically involves interaction between the objects, causing that state to change. We have seen lots of examples of procedural or functional programming in the first part of the course. Now we're going to spend some time exploring a second style, which is object-oriented programming. Today, we'll explore a relatively simple object-oriented system implemented using message-passing objects, very much like our message-passing const example. In a later lecture, we'll explore a more sophisticated object-oriented system and scheme. To discuss object-oriented programming, we need some terminology. In an OO, or object-oriented system, we will talk about a class and an instance. A class describes a set of objects with common behavior. For example, const in our previous example was a class. By convention, to use a class, we will have a maker procedure that creates instances of this class. An instance will be a particular and specific object generated by a class. For example, foo or bar in our earlier examples were instances of the const class. An instance takes messages in the manner defined by the maker procedure and uses them to manipulate the particular values of the instance. So we expect as a consequence to have lots of instances of each particular class in our system. So here is a good way to conceptualize these ideas, and in particular the differences between them. First of all, associated with the class we can draw what we call a class diagram. This would contain information such as the name of the class, for example a pair, information about the private state that belongs to instances of that class, in this case x and y, as well as what messages, public messages in particular, that this class recognizes. Here it would be things like car, could, or pair, question mark, set car bang, set could or bang. And note that these public messages define the interface to the class objects. So this class diagram captures the information about a class. Its name, the state information that's captured within it, and the messages that it accepts from people outside of it. Thus, in our example from before, const defines a class. Defining const xy to be that lambda of whatever is our way of constructing elements from this class. And that leads exactly to the idea of an instance. When we use the maker associated with this class, in our case it was const, we create particular instances of this class. We create examples from this class. So we'll represent this by an instance diagram. Within that diagram we'll have information, the type, which is the type of the class of course, as well as specific values for the internal state. And note that these could themselves be other instances of classes. So if we define the example expression shown, in our instance diagram we create two instances of the class pair, both created by the maker procedure const. Within each, we have bindings for, or specific values for, the internal state associated with each instance. Notice how these bindings can be simple values like numbers, or pointers to other instances of classes. So we see that a class defines a set of objects, and an instance is a particular version of an object from some class. So how do we use the ideas of classes and instances to start designing a system? Let's suppose, as an example, that we want to build a simulator for an amalgamated space wars game, stealing ideas from any different fictional worlds. It would have ships that could fly through space, land on space stations, shoot other ships, and so on. We can start by asking ourselves, what kinds of objects do we need? That will tell us what kinds of class we need, and what state information is needed for a class, and what interfaces between classes are needed. It might say, for example, that we want some ships. Since ships will need to move, this helps us decide what kind of state a ship will need. Thus, we begin thinking about the system in terms of what kinds of objects and what information associated with those objects we want. We can then extend this to start thinking about particular instances of objects. How many, what state for each, and so on. So let's see how the idea of a class and instances of a class can be used to design an object-oriented system. We will use our Space War simulator to explore the use of classes and instances of classes to build object-oriented systems. The first class of objects in my system will be ships. So here's a procedure for making instances of the class of ships. This maker procedure defines the actual class. Given the idea of a ship, we can turn to the question of what behavior we want for instances of that class. Clearly, a ship needs to be able to move. Note that this then tells us that we will need some information about where the ship currently lies and how it is moving as part of the class definition. In this case, we choose to pass that information in when we actually construct the instance. So this tells us we will need position, velocity, and maybe some other things as inputs to the class constructor. Actually, we are getting our local state variables in a sneaky way here. We know that in order to move, we need to have that kind of information as part of the class. But in fact, we could have created a constructor with no parameters and simply have had within it a let clause that contained initial default values for the position and velocity. Notice how thinking about what we want our objects to do helps us to decide what information should be captured as local state and what information should be passed in when we create instances of this class. And what about the class itself? When we use this maker procedure, it will return an instance of a ship, which will be represented by one of these message passing lambdas. Note the form. It takes as input a message, and either returns information about the state of the ship, or causes one of the internal procedures to be executed. This looks a lot like the generalized form we used for our const pair earlier. Similarly, we will have internal procedures for manipulating the data values, very much like our const example. The only other thing to note is how the last clause of our message passing procedure is a bailout clause. It says, if you give me a message we don't recognize, I'll let you know so that you don't try to do something you can't. Thus, here's the definition of a class, a maker procedure that creates ships. So let's gather that together in our class diagram. We have now a class diagram of a ship, and it has a set of variables, position, velocity, number of torpedoes, as we saw, and it has messages for methods to manipulate those variables. And as we said earlier, those messages define the interface to instances from this class. So now, let's make some instances. Let's define Enterprise to be an instance of a ship. Notice how we give it a particular position, a particular velocity, and a number of torpedoes. Similarly, we can define Warbird to be another ship. Again, notice how we create the initial position, velocity, and number of torpedoes for that instance. Of course, we're using some abstraction for vectors here. We don't really care about it. It's just going to make vectors for us and have us presumably have some way of getting the pieces back out. Key thing to notice is using that maker procedure for a class, I've made two different instances of that class. They have their own state information captured within them. They have their own procedures for manipulating that state information. And the interfaces to them are defined as the set of interfaces from the class itself. Each of these objects will accept the same set of messages and cause their own internal state to be changed. So let's check this out. Let's use our environment diagram to see how our little system evolves. And I want to stress, we want to both watch the idea of instances of classes and classes themselves as a general notion, as well as looking at the particular implementation we're using here. So let's look at what happens if we evaluate these three expressions in order to see how our classes create instances and how those instances keep track of state information that can be updated as we carry our simulation forward. First of all, we're going to use our makeship, or maker of instances of a class. So we use makeship. And evaluating that particular expression, we know does the following. Makeship is a procedure, so applying it creates a frame in which the formal parameters, position, velocity, and number of torpedoes, are bound to the values of the arguments passed in. In this case, a couple of vectors and a number. This is just standard application of procedures. Having created that frame, we then evaluate the body of the procedure with respect to that frame. And notice what that does. There are a couple of internal definitions. We define move to be a procedure. And the key thing to note is that that procedure has as its environment pointer this frame, because that's where we're evaluating it with respect to. Thus, move will be a name for an internal procedure which will have access to things like position and velocity because its environment pointer points to it. Thus, we see that those two internal defines create bindings for other names, move and fire torque, within that frame that happen to point, in this case, to local procedures. And thus, this overall frame contains the information about this instance of the class, the state variables, and the local methods that will be used to change those state variables. Having evaluated the local defines, that is, having created the local methods for this instance, we then evaluate the rest of the body of this constructor, make ship. And that, of course, evaluates that last lambda, creating a procedure object whose environment pointer also points to this frame, because we're evaluating the body there, whose parameter is the message, whose body is going to be the thing that does the right stuff with the message, and a binding for enterprise in the global environment is created to that object. So this creates, as before, one of these nice procedure passing objects. It has local state, including information about what procedures to use to cause that state to change. Now, let's ask this particular instance of a ship to move. That says send the procedure representing this ship, the message move, and we know from the code on the previous slide, that reduces to evaluating the actual procedure move with respect to this frame. And what does that say? It says apply that procedure. There has no arguments here, but we still create a frame. We just don't bind anything in it. And relative to that frame, we evaluate the body of this internal move procedure. And that says, gee, change the position. And of course, evaluating the body of this procedure causes us to mutate the current position to a new position by adding the vectors together and creating a new one. So just like we saw in the const example, we now have changed the state, which means if we ask for the new position of enterprise, we will get this value of the vector out and return that as the appropriate thing. So what we see is our local instance of a ship now captures within it state information and procedures to change that state information. And the actual object, this instance, is a procedure that takes messages and does the right thing. One of our claims for object-oriented systems is that they enable relatively easy extensions to a system. So let's try this out. What kinds of things could we add to our system? First, we could add new classes, for example, a space station class, which should have a different behavior from ships. For example, space stations may not be able to move, while ships can. We could add more than one additional class. Perhaps we also want torpedoes to help make the Space Wars world entertaining. And we might want to add a display handler, something that draws the position of our objects on a screen. This might be implemented as a procedure, since not everything has to be an object in our system. To add a display capability, we will need to modify our classes so that every object can display itself on demand. With this framework for modifying our system, let's see how one goes about extending object-oriented systems. If we add space stations to our system, we will have a new class diagram. In addition to our earlier class, we now have a class for space stations, with some state information and some methods for manipulating that information. Notice that as part of our design, we also add another new thing to both this class and our original ship class, a method for handling display. Now, watch how we can add new instances to our system and how we can easily return to our original design and modify it to add new components and methods. To start, here is our maker procedure for the space station class. Here, the only local information is position, and the instances will recognize two methods. Notice how we can add methods that simply execute a procedure without returning a value, such as in the display method. Here, draw is used for the side effect of graphically displaying the station. And to add some spice to our system, we will let ships shoot at each other, so we'll add a new class, a torpedo. To add torpedoes, we again need to update our class diagram, and here it is. Notice that this class has a lot of information similar to that of ships, a point to which we will return later. The top level point to note is how our design is evolving. We started with a single class, and have now added new classes as our desires for this system expand. Each class has a set of local state variables and methods that it is capable of handling. The other change to our class diagram is the addition of various new methods for existing and new classes. For example, we also add a method explode to implement new behavior associated with torpedoes, or the effect of torpedoes on ships. Again, note how our design is evolving. We can add new classes, and we can extend existing classes by adding new methods as our desired behaviors for the system demand them. Here is a corresponding maker for torpedoes. It has a similar structure to what we are used to. Ultimately, we are making a message handling procedure with embedded local state, local procedures, and public methods. Here the explode procedure hints at some subtle behavior. When a torpedo explodes, it is destroyed. So in our simulation world, we may need to manage this, such as by a remove from universe procedure illustrated here. Indeed, a typical application of object-oriented systems is to create a simulation world and then to run that simulation. Some additional machinery will certainly be needed. For example, we may need a way to keep track of the instances in our world, such as by using a global the universe list. In addition, there needs to be some controller or clock that invokes methods on instances in the world, perhaps in a round-robin fashion, perhaps in a random fashion. Here we have sketched the basic outlines of an object-oriented system and supporting mechanisms like a clock. Use your imagination and picture running the clock to generate awesome graphic evolving images of spaceships firing torpedoes at each other in the shadow of a large space station. Let me remind you of what we've seen so far. We are trying to organize a large system around a collection of objects. An object can be thought of as a smart data structure, a set of state variables that describe the object and an associated set of methods for manipulating those state variables. We expect our systems to have many different instances of the same kind of object. For instance, think of a bank system in which we might have different accounts. Each account would have a set of data values: current balance, overdraft protection, pending deposits. Thus, there's the notion of an account as an abstract structure, and there's the idea of different specific versions of this abstract structure. Thus, we make a distinction. A class will define the common behavior of a kind of object in our system, the collections of things that are going to behave in the manner defined by those commonalities. Instances capture the specific details of an individual version of that class. In our simple Space War system so far, we have class diagrams such as those shown here. We have a class for ships, a class for space stations, a class for torpedoes, and some other classes that we've not shown here. Recall that for each class, we had two sets of things: internal state variables, which characterize the state of each instance of the class, and a set of methods, the things that the class was capable of doing. Those methods often were characterized by the instance accepting a message of the same name, then performing some interaction between different objects within the system, or changing the status of the internal state variables of an instance. In order to make a point, I have changed slightly my definition of a torpedo. Last time, a torpedo just used a position and a velocity, and it moved until it hit something, at which point it exploded. A smarter torpedo might explicitly seek some target and use a state variable like a proximity fuse, so that when the torpedo got close enough to its target, it would explode. One reason for introducing this is to notice that state variables within our instances could actually point to other instances. So in the class diagram, we would indicate this with a state variable for a target that points to another class, a ship in this case. However, the real point to which we want to draw attention in this diagram is the commonality, particularly the commonality between ships and torpedoes. Note that both of these objects can fly. They both therefore have state information about position and velocity. They both have methods that deal with position and velocity. Thus, they have a lot of things in common, as well as having a few distinctive properties. We know that a common theme in this course is capturing common patterns and abstracting them. So the issue here is whether we can do the same thing in an object-oriented system. Can we take advantage of the fact that torpedoes and ships share a lot in common and use that to build more modular systems? Conceptually, we should be able to do this. Without worrying about implementation details, let's first pull out that common pattern in our class diagram. Here's an abstraction of that common pattern, a new class called a mobile thing. It has two state variables, position and velocity, and it has some common methods for dealing with those variables. These variables and methods will hold for any mobile object, and thus this defines a new class. Given that new class, we can now create specializations. We can create a subclass. A torpedo is a particular kind of mobile thing. It has all the properties of mobile things, but it also has characteristics that are particular to torpedoes. Similarly, a ship is a kind of mobile thing. It's a specialization that has, in addition to the properties of mobile things, other characteristics that matter only to ships. As we start designing our system, we can begin to put together hierarchies of class diagrams. We have base classes like mobile things. We also have some specializations or subclasses, so that, for example, a ship is a mobile thing and should therefore inherit the state and behavior of a mobile thing, as well as having its own properties. In the other direction, we say that the mobile thing class is a superclass of the ship and torpedo classes. Now we can start building a broader set of designs in which we have hierarchies of information captured in different specializations of different classes of objects. And as we fill out our class diagram, we will have different relationships between the classes. Torpedoes, for example, can have a class as a link. Targets are always going to be elements of the ship class. Note that one of the advantages of creating superclasses is that we can nicely isolate the code for the methods of the superclasses, so that if we want to change one of those methods, we only need to worry about the implementation of the superclass, not about all of the specializations. If, for example, we decide to change how things move, we don't have to search for all the move methods in different subclasses. We need only change the method in the superclass. This gives us, of course, a nice modularization of the system by isolating the common methods in a single place for easy maintenance and change. To summarize, we've explored several of the basic elements of object-oriented programming. Objects are now smart data structures. They have both state information and methods to manipulate state or implement other behaviors. The class specifies the common structure and behavior of instance objects of that class. We've briefly introduced the idea of inheritance to share structure and behavior between classes. Today, we've looked at message passing objects to implement a simple OO system. Next time, we'll look at a more sophisticated OO system and scheme, in particular to incorporate inheritance that we just touched on today.